who can't be here for a good reason, and for the others that are missing for bad reasons, they can do it too. You have a base map, which is the 1958 topographic map. And on that, what I've drawn are the riverbank margins on the eastern side of the river. Okay, so this is time one. You then need to transfer the margin of the bank in 2015. I'm just doing it on the top for illustration purposes. Okay, so that's step two. Then you'll need to determine the rate of change. So for that, you need a distance and a time. You know what the time interval is. It's 1958 to 2015. Now, the distance depends on how you draw this line. Okay, and I could have drawn it kind of at perpendiculars. Let me see if I can get this. Perpendiculars, or I could draw it more like this. Okay, and that depends on whether or not the river is migrating through expansion or translation. There's different ways in which the river migrates, but the difference isn't going to be much. So whether or not you draw a vector that's perpendicular to the riverbank or in one general direction, either one's fine. I actually think one general direction is probably more indicative of the way this particular meander is running. So now you've got three distances for three lines, and I've used three just to try to get a sense of how much variation there is. Okay, I wouldn't do more than three, but one isn't going to give you the area that you need. Okay, so kind of at the middle and either end. And of course that distance will be determined based on the graphical scale. Okay, so now you had a distance, you divide it by a time, that's a rate. You take that rate at the same direction and you multiply it by 60 years. So now you've got the distance from 2015 to 2075. That is the location of where you think the riverbank will have eroded in 60 years. Okay, that is the river erosion hazard area. Okay, so that's what you want to have on your map. Now, obviously, you want to do it for the southern side as well. I asked you to do a green area for deposition. I'll tell you what, don't worry about that. Recognize that deposition is going on the other side of the bank. But my main interest is what's going on in the subdivision. And so as you'll see, there's no deposition going on in the subdivision. So just focus on the erosion and the river erosion hazard area. Okay. So the first thing, is that part clear? Does anybody have any questions? Okay. Now the second thing is you need to evaluate that both the flooding and the erosion, particularly the erosion, in the context of the levees that were proposed by the Corps of Engineers. And there's two levee systems, Levee A that protects sections 1, 2, and 3, and Levee B that protects section 1 of the subdivision. Okay. Now remember also, as I said, the Corps of Engineers isn't going to build something unless they think it'll last for at least 50 years. Okay. Now the report to the mayor is a 1 to 2 page typed report that would be read in a council meeting, where you will first of all discuss the frequency and magnitude of flooding based on the first part of your assignment. Okay. Now in particular, focus on those two floods and the recurrence interval of those two floods that caused so much damage. Because remember, one of the questions might well have been, were those 100-year floods? Were they 1-year floods? In other words, how likely is it that flooding is going to occur again? The second thing is, how likely is it and where will flood-induced erosion occur? And that is, of course, based on part 2. And to illustrate that, you will attach the maps of erosion. And I said depositional change. Don't worry about that. Okay. You will make a specific recommendation as to the suggestions by Corps of Engineers, what's realistic. Okay. You'll also include any assumptions that your conclusions are based on. Okay? So are there any questions about the letter? Okay. All right. So that's basically what you need to do. Now, the last thing, let me just mention very quickly that almost everybody did fine on the flood frequency part, Part A. Particularly, almost everybody can rank something from large to small. But there was a counting error on a few of you where you had the wrong numbers of years. Okay, so that put you off by 1. Turns out it didn't make any difference when you plotted it. Okay, but remember, recurrence interval is n plus 1 divided by m. Okay, the other thing that a fair number of you did, you forgot how to plot on log paper. And so let me just remind you, and you'll get, you can come see them, or I'll even give them back to you if you like. The log, where it does 1, then 2, and it's broken up into a bunch of little things. If this is 100, this is 200. A lot of people put that as 120. Okay, 120 is down here. 150 is there. This is 200, whatever the unit is. That's 100. Okay, so just remember how to plot on logs. Okay. The last thing is a couple of you plotted 1 over recurrence interval divided by recurrence interval. Whoops. Well, I'd suggest that doesn't really make any sense. You don't plot the reciprocal of something against something. Or if you do, you're just going to get a parabolic line or logarithmic line. You need to plot discharge against something, in this case recurrence interval, and of course most of you also figured out that that's really the same thing as probability, just listed on the top. Okay, so that's all you had to do for plotting discharge against probability. You've already done it when you plotted that. Okay, so any questions about that? Okay, all right, well then let us start talking about minerals and mineral resources. When I talk about resources, I need to make sure you understand the distinction between a resource and a reserve. A resource is just something that's naturally occurring and is a potential value. A reserve is a subset of the resource that can be economically and legally used or obtained today. Okay? And so to illustrate the distinction, imagine that the area of this square, or if you like, imagine the volume of a cube, is all the possible elements of something, maybe gold, okay? Or it could be oil. You know. And think of your degree of certainty. Do I know it's there? Can't produce it today, so there's going to be a distinction between resources over here, both hypothetical or speculative, and reserves. But I not only have to know that it's there, I've got to be able to economically produce it. So is it economic? Okay, well, if it is, it's a reserve. Now, in this particular example, is it marginally economic? Well, okay, it's a marginal reserve. If it's sub-economic, I can't afford it, it's not a reserve, it's a resource. Okay. Now, another example might well be, can I legally produce it? And if you think about something like offshore oil, is it legal to drill in offshore oil? It depends on which state you're in. So if it's illegal, if it's in a national park, you may know it's there. You may have the technology to produce it, but you can't legally produce it. So it's not a reserve, it's a resource. Now, the other thing to recognize is that although a reserve is a finite volume, we've talked about this before, a resource is a finite volume. We're never going to create any more gold. We can enlarge or reduce the size of the resource, the reserve rather, I'm sorry. get that straight before the exam. And because we can change the economics, we can change the technology, and we'll see examples of that. Okay. Now, when we talk about resources in general, we recognize the distinction between renewable and non-renewable. We think of renewables that are being replenished potentially as fast as we're using them, or faster. Okay. Non-renewables takes too long. But it's actually a little fuzzy here. So if you recall, is water a renewable resource? And of course, we typically say yes, unless of course it's groundwater that was put into the ground 18,000 years ago, and we're taking it out faster than it can be recharged. In that particular case, we're treating it as a non-renewable resource. So there's a variety of issues like that. We can actually begin to imagine a spectrum of semi-renewable resources. Okay. When we talk about types of resources that our scientists are interested in, we've got mineral, energy, and water. We've talked about water. We're going to talk about minerals. When we talk about minerals, we're actually using a somewhat broader definition, metallic and non-metallic minerals and rocks. So we're going to kind of add rock to that type of resource. And energy resources will include in our last set of lectures. Now, when we talk about mineral resources, we're really interested in ore deposits. And so that's a mineral or a metal that we have that we can produce using current technology and current economics, and I would add legal conditions. So an ore deposit is really simply a mineral or metal reserve. Okay. Now there are some non-commercial ore deposits that they sometimes call proto-ore. That's kind of like the sub-economic. Okay. And it might be because it's just too expensive to mine it or to transport it, or the prices aren't right. So there are things that might become ore if things change, which is, say, they're a resource, they're an ore resource, but maybe someday they'll grow up to be an ore reserve. Okay. Okay. So when we look at these non-metallic and metallic resources, these ores, well, it turns out stone is the biggest one of all, at least in terms of weight. And we've got copper in the metal. We've got metals here, and we've got non-metallic here. We use a whole bunch. This is a per capita volume, or actually a per capita weight. So we use a lot of things per capita. And an awful lot of them are construction materials. Okay. If you look at the volume of raw materials that are used in the United States, the main increase is in constructional materials. Okay. And so we'll talk a little bit more about that later. But one of the things we are interested in is what are we using, how, and where does it come from? And of course, what are the environmental implications? Okay. Well, these are just some metals for the most part. Well, minerals, let's say, some of which are metals. And that's our consumption as a function of global production. This is our percentage of population. We use a lot more than our proportional share, but then we produce a lot. So I'm not saying that's good or bad, but you might notice that in some cases we use over half the world's lead, even though we have 5% of the world's population. So hopefully we have a lot of lead, unless of course we don't. And then the question is, where does it come from? Because we're using a lot of it. So we need to think about where it is, that is where each of these elements are. How do we get it out, and who's using it, and so what? Okay. Well, it turns out if you look at the U.S. reliance on imports, the lines all the way to the right say we're 100% reliant. That means we don't have any of the things we use. Okay. And if we look at those things that we have to import 100%, okay, there's a whole bunch of things, and you don't have to know what they are, But there's a whole bunch of things, and a related question is where do they come from? Well, among other things, China, 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 China. Have I mentioned China?
Yeah.
China. Okay. Well, you know, the point is that we are very reliant on a few countries that this reliance determines our political and economic interrelationships. And so we cannot separate China's politics from China's natural resources, particularly when we talk about natural resources that we use and we don't have any of. In fact, if you look at the proportion of global production of minerals that are of interest to Europe, and I would add they're interested to us as well, the purple is China. This is 50%. And in some cases, like heavy rare earths, they have 100% of the world's resources. Okay? So when we think about Saudi Arabia in the Middle East as being dominant in terms of things like energy resources and oil in particular, but in a lot of ways, they're just amateurs compared to the volume, or better said, the percentage of important minerals that are owned by just a few countries. Yes, ma'am.
Yes, and actually China is mining out a lot of land in Africa, so they're trying to control the minerals there as well.
Absolutely, absolutely. The world, there's a lot of geological geography that is determining geopolitics. South Africa is another major one that we've had mixed relationships with. The Democratic Republic of Congo. A lot of the, as was suggested by Barbara, a lot of the interaction between Europe, America, and China in Africa geared towards things like diamonds, rare earths, etc. Okay. Now, we're less dependent on some other things, which is, say, we provide maybe 75% of some of the minerals, and a few things, again, you don't need to know this, this is for your reference, but a few things that we are 100% reliant on, okay? And some things less than 25%. So as we go through this long litany of different types of minerals and their uses, and we're not going to go to any detail in that, but if you were to, you would realize that we're fine for sand and gravel and clay and surprisingly aluminum, but we are in sad shape for rare earth elements, etc. So a lot of what we do depends on others. Okay, this is an example of rare earths, and this is the production of rare earths, and this is China. This is the U.S. Notice we kind of quit producing about 10 years ago, and this is the rest of the world. Okay. These rare earth elements are used for a lot of things. Catalysts, metallurgy, ceramics. They are surprisingly useful, surprising in the sense that you've probably never heard of them, or many of you have never heard of them. And if you look at China's share of metal consumption, aluminum, copper, lead, nickel, tin, and zinc, wow. Whereas the rest of the world has been gradually reaching, if you like, a steady state, China is taking off. So what this means is China is a competitor. On the global scale, India really not nearly as much for resources that we're also competing for. And this would also hold for oil and etc. Okay? When you look at the amount of certain elements that China is consuming, in a lot of cases, it's 25 to 60% of the world's materials. Okay, so China is growing very fast. It's an economic giant, and it's causing a lot of issues, not the least of which is the amount of greenhouse gases, but also our political relationships as well. Now, one of the things to think about is how does an element become an ore? Okay. Well, of course, first of all, they have to be present in a mineral. And so let's just take some metallic minerals, gold, mercury, lead, copper, iron, and aluminum, and think about where they occur. So gold is a funny mineral. It does not like to associate with anything. It's one of the native elements. It tends to stay in solution as long as it can, and then finally when the last gasp of magmatism comes out with a siliceous liquid, it finally precipitates out, and so you get natural occurring gold in quartz veins, etc. So natural concentration is very low. Because it's so expensive, you don't need a lot of it, but because it's so low to begin with, you've got to increase the concentration 2,000 times. So you need to think about how am I going to do that? Well, you can do it as a miner or an engineer with certain types of techniques, but nature has done it too. So we're going to look at what are the natural concentration processes. Mercury, oh wow, you need 10,000 times. Lead, high. Copper is kind of an interesting one. It's about half of 1% in copper mineral when a natural occurrence. You don't need to increase it too much, but let's say 80 to 100%. And by the time we get to aluminum, aluminum is the most common element in the crust. And by the way, where does aluminum reside mineralogically?
In the mantle.
Beg pardon?
In the mantle.
No, the mineral. It's actually the most abundant element in the crust.
In muds.
In
muds.
Mud? Nah, a little bit, but not much. Feldspars. Feldspar. Not only is feldspar the most abundant mineral, but it's an aluminum silicate. Okay. So it's number 8. Actually, iron is number 5, but a lot of it is farther down. Doesn't have to be concentrated a whole lot. Concentration factor 4. And good news, we don't have to do much to do it. We just let the bauxite formation do it for us. So we're going to look at these various concentration factors. And the processes by which concentration occurs has to do with, at least in part, the geologic origin of those deposits. So we've got minerals that are the result of igneous activity, metamorphic activity, and sedimentary activity. So these are all processes that we're going to look at in terms of how we as geologists might explore for something, where it would occur, and as we'll see, the extraction techniques and their potential environmental impacts. Okay. Well, let's look at diamonds for a second. The diamonds are the result of igneous activity. They crystallize, but they are a high pressure, high temperature polymorph of carbon. And so this is a phase diagram. In order for a diamond to form, you've got to be below this line, which means, wow, here's the geothermal gradient. So this is kind of where the Earth is at different depths, how hot it is. So diamonds are forming down in the mantle. They don't form today. Yet we're clearly not mining them in the mantle, so we need to figure out a way of bringing them to the surface. And we do that through a series of kimberlite pipes. Kimberlite pipes are these conduits through which there are major eruptions that came up from the mantle, but still were very deep in the crust. Okay. So where are you going to find those? Well, I would look for places where most of the crust has been eroded. And so those are going to be the shields, like the Canadian shield, the South African shield. So the first thing is we need to find a place where most of the overburden has already been eroded. Okay. Then we've got this kimberlite that's all in here, breccia, and intermixed within the kimberlite are these diamonds that were brought up from the mantle. So we could initially start to mine it through open pit mining, but eventually it gets too deep, and so then we start mining it through underground mining. And of course, the great kimberlite pipe in South Africa is almost a mile deep. It's the deepest open pit mine in the world. Now, just before I finish that, let's look at one other thing. These diamonds actually have been eroding. And so if we just had a process to concentrate them, the erosional diamonds, then that would be nice. And it turns out that diamonds are heavy. They have a high specific gravity. And so they tend to be concentrated in what we're going to call placer deposits. We'll talk about them in more detail later. But basically, the second place you look for diamond, besides kimberlites, is areas where they've been concentrated. And in South Africa, that's along those shorelines. So if you could determine the location of old beaches, then you have the possibility of seeing a second mechanism to concentrate diamonds. Okay. Now, if we look at production of diamonds, you would not expect Canada necessarily, in part because they really didn't produce any diamonds until the late 1990s. And the thing is, people from South Africa and others thought, you know, this is geologically, the Canadian Shield has a similar setting as does South Africa. So there ought to be kimberlite pipes. The problem is kimberlite's all brecciated up. That area has been glaciated. And so they're mainly, if they're there, they're going to be under lakes. So what do? You start looking for things. Well, this is a fascinating story that I'm only going to touch on just a little bit. But what a couple of geologists started to do was to say, what are the minerals that are more common than diamonds but occur as accessory minerals in kimberlites? And so they started looking for those. And they found them. So they said, aha, there are kimberlites someplace in the shield. And so then they started looking at the patterns of glaciation. And so they said, okay, if I've got a pile of stuff from a kimberlite here and the glaciers came in this direction, I'm going to start looking for them going up glacier, if you like, until all of a sudden they don't have it anymore. And then I know I just walked over or flew over kimberlite. And it turns out that these production rates now, about from 12 to 15% of the world's diamonds are now coming from Canada, including perhaps most of the gem quality diamonds. And one particular mine, just to give you an idea, is an open pit mine with 6 or 7 million carats of high quality diamonds, and they're about to go underground as well. So this is a newcomer on the field to rival South Africa. But again, an interesting geologic story. Now, plate tectonics controls, to the largest extent, igneous activity. And the extent to which we're looking at igneous processes that are mineral forming or ore forming, look at divergent and convergent plate margins. And again, we're not going to look at any detail in these, but for example, when you look at copper or zinc or beryllium or gold, they tend to be concentrated, most of them at least, in the west, looking at the Laramide and Cordilleran orogenic events, the plate convergence between the Pacific Plate and the U.S., or the Appalachians, which was a convergent plate margin back earlier. And then there are just a few funny little examples like the Midwest, where we have some very old hydrothermal deposits. Okay, and so I'm just going to look at one example, and that's a porphyry copper. And porphyry coppers form basically within the magma chamber that's the result of subduction associated with convergent ocean-continent convergent margins. So that series of andesitic volcanoes or stratovolcanoes that we talked about along the Cascades are underlain by porphyry coppers. Okay. Now, they're not exposed in the Cascades, but as we'll see, they are exposed in a lot of areas. So if you look at where porphyry coppers occur today, among other places, look at along here, these, and here's convergent margins here, convergent margins along here. 60% of the world's copper reserves are these porphyry coppers, okay? And they are preferentially formed along these convergent margins, okay? So let's just look at our porphyry coppers, and interestingly, they're sitting over here. So you might ask, why do we have porphyry coppers in New Mexico? And the reason simply is that 35 million years ago, that was a convergent margin. It was a very gentle slab, so there was a pretty good distance between the volcanoes and the plate margin. But that was an andesitic volcano, and the roots of it, which are now exposed today, is this magma chamber. Okay? So interspersed within, disseminated within those magma chambers is copper, but a very low percentage. Okay? So we need to figure out how to, initially at least, how to concentrate it. So we're going to actually think about a weathering process, and it turns out that weathering process is both a boon and a bane. So it's oxidation, and in particular we're going to look at oxidation of pyrite, which is an iron sulfide, and it creates limonite, which is an iron oxide, and sulfuric acid. Now, first of all, we don't mine pyrite, or at least we don't purposely mine pyrite. It's not an ore of iron. It's not an ore of sulfur. It is an accessory mineral. But the problem is you can't mine for copper without getting pyrite. And I'll also add, there are many areas where you cannot mine for coal without getting pyrite. So we tend to oxidize pyrite. Okay? Now, it turns out the oxidation of pyrite is a naturally occurring process that helps us to concentrate copper. Okay? So the first thing it does, it creates sulfuric acid. And then the acid tends to leach that dissolved copper from the upper part of the magma chamber. And then as that acid, as that dissolved copper migrates down, it gets into a reducing condition where it reduces to chalcopyrite. And chalcopyrite is a copper sulfide. So notice we started with pyrite and we ended up with copper sulfide through a combined action of oxidation and reduction. Now also notice we're still creating SO4. Okay. Now imagine that this whole thing is a large magma chamber. Okay. Now it has been weathered. It has been oxidized down to some depth, which is the water table. This is in an arid region, so the water tables may be 1,000 feet below the surface. So at the very top, we have a feature called a gossan, which is a weathered cap. It tends to have a lot of iron oxides. They're insoluble. But then we have a leached zone, and it's kind of like the B horizon. I mean the A horizon, that leached A horizon that's maybe a foot deep, except this might be 1,000 feet deep. And then right in here, that leaching, you begin to have at the top of the water table a concentration of oxidized ores. So these would be our copper oxides, malachite, things that look green and blue, the real pretty ones. Okay, but down here, we've enriched the sulfides by reduction. So this is the zone of what's called supergene sulfide enrichment. This is the chalcopyrite. And it's a miserable, sooty-looking, darkish mineral that seems to have no value except there's a lot of copper in it. Okay, so when you think about exploration and also production, where are you going to look? Well, it turns out that the first copper we would used to mine is here, the oxidized zones. Okay, and we found the near surface ones, but then we realized that, hey, there's a lot of them at great depths, but that means underground mining. Okay, and you could also try to get into here, this sulfide zone. But there's a lot of ore down in the primary zone. So we have a supergene and a hypogene. Super meaning the top, hypo below. The problem is, this is the disseminated copper. It's been concentrated by all this leaching. So this is the concentrated zone. This is the disseminated zone. And it's deep and it's low volume. This, by the way, is now my scribbled up version of what a Gaussian would look like in that bleached zone. Okay. Well, turns out that now we've got the technology to literally dig it out of the ground. So we use open pit mining to get down to this hypogene core, and we can concentrate it by a variety of processes. And so whereas it used to be that we needed about 2% to make it economic, now it's about 0.25%. Now it's economic to produce that copper from the disseminated zone. Okay. But now we've got a couple of issues, not the least of which we've got a big hole in the ground, but we also have a tremendous amount of mine waste, because if 1/4 of 1% is ore, then 99.75 is waste. And so we have a huge volume of waste to deal with. Okay. This simply looks at actually I'm going to skip this, but it basically says that if you can handle more and more tonnage, you can reduce what's economic to a very small percent. And so the ability to have these trucks that are as big as this room, mining has really changed the economics. And so here, for example, this is what used to be economic in 1880. It needed 3%. By 1970, you needed 1/4%. But now it's increasing again. So the first thing is this was increased efficiency. So we could produce more for less. And that was basically the going from surface mining and underground mining to open pit mining. That increase more recently has been the fact that so much came on the market that the price decreased, and it got increasing cost because the price was less, and competition. So we begin to see that technology is just one of the factors that determines what is an ore or a proto-ore. Okay. Now, one of the things I would mention, I'm going to skip this. This is just remote sensing data. The good news is the types of alterations that occur, not just the Gaussian, but other types of mineralogical alteration that occurs in porphyry coppers, we're able to increasingly delineate using advanced remote sensing techniques. So literally in almost 50 years ago, we were using multispectral data to try to locate these porphyry coppers, and it actually was going to be my first dissertation topic until I decided I wasn't that interested in it and did something else. So what are some of the environmental issues? Okay, well, let's look at all that waste, and actually let's just look at the waste and disposal, the refinement, the chemicals. All these produce waste all the way to the products. Okay. Now, we'd like to recycle some of these, and so we do recycle copper, but we've got disposal problems throughout the entire system, okay, from extraction to what do we do with the cars, okay? So let's just look at some of the issues. Well, here is an issue that we talked about earlier, and that is collapse or subsidence. This is over an underground copper mine. We see this is a problem with coal mining and other things as well. So certainly subsidence, a problem. What do you do with the spoils banks? Now again, this is a coal mine, and part of what I'm getting at is that the problems of copper mining are shared by a lot of different types of mining. Well, we try to revegetate. And ironically, in Texas, coal mining does a pretty good job of reclaiming the land, but that's in East Texas, where it rains a lot. Most of the porphyry coppers are in the arid Southwest, where it doesn't rain a lot, and so you basically have big mountains of non-reclaimable waste material. Now, the other problem with this waste material is that one of the waste byproducts, is pyrite. We don't want that stinking pyrite. But what happens when rain comes down and we've oxidized the pyrite, we've got water, we've got SO2, we've got acid water, we've got acidic mine waste. So the acidities for these mines, as well as other dissolved minerals, you can see the iron that's dissolved in there, causes a tremendous amount of water pollution from the drainage of these wastes. Okay. The other thing is, another process of oxidation is when you smelt the ore. So you're burning the ore, that's oxidizing it, but of course there's still going to be sulfur in there, and so you are producing SO2, which combines with water to form H2SO4, sulfuric acid. In fact, if you look at this, this is an old picture. You would no longer see this happening today, but notice the plumes that are coming up, and look at that plume is sinking. That's never a good sign, because that's not water vapor, that's particulate matter, and the water vapor that is coming out was full of SO2. And so when it rains, you have acid rain as well as acid mine dumping. So look at all the problems that you've got when you are producing or oxidizing sulfides. Okay? You can also get nitrogen oxide, but I'm interested mainly in sulfur dioxide. It can precipitate as acid rain. We've also got waste material that's coming in and contaminating aquatic systems. One of the strange things about looking at rivers downstream from some of our major river source or waste sources is they're very clear. They look like they're just beautiful, except that they're dead. There's nothing in it. And so there's no algae, there's no life. And so the impact is huge. And of course, acid rain in terms of affecting monuments, croplands, etc. The Adirondacks, pure water might be here. It went from the 1930s to 1975, went from about neutral to an acidity of 5. In some cases, the pH is even higher. And we literally have areas downstream of smelters that are wastelands. Now, an interesting issue, though, came up, and this is typical of issues that we have with respect to regulation. Remember, the EPA was developed as part of our National Environmental Policy Act in the early 70s, and at about that time they started looking into this problem of SO2 coming out of copper smelters. So they said, you guys got to quit this. This is bad stuff and you need to quit it. And of course, the immediate response from the copper companies was, well, we can't do that. It's uneconomic. You put us out of business. All these people are going to be unemployed. Babies will die. You baby killers. And so they said, well, figure it out. Okay. Well, one of the things that you need to think about is how do we get that copper out? And one of the ways is leaching it. So when they take the high-grade copper out and smelter it, high-grade ore, the low-grade ore, they actually apply sulfuric acid to it. And so they actually remove the copper and then reprecipitate it in these great big plates. And what they do is they put a plastic liner underneath all this waste, and then they sprinkle it with sulfuric acid. Well, what they did was they put sprayers, what they call scrubbers, in the chimneys, And so as that SO2 is coming out, they sprayed it, and so they extracted it as H2SO4. And then they used it to leach out the material. So they went from buying H2SO4 to selling H2SO4. Okay. And they not only cleaned up the air, but they saved money. Now, I won't say that all environmental regulations end up that happily, but the fact of the matter is, this is part of what we try to do, to try to figure out, is there a win-win with respect to environmental regulations and environmental impact. Because of that, we've seen the production of sulfur, which is used for a lot of things, from medicines to a lot of industrial purposes, has remained relatively constant, but the recovered portion is basically from scrubbers. And the fresh process, which is a process that we talk about from dissolving sulfur in salt domes, that's been decreasing. So we've actually been able to replace one source of sulfur for another. Okay. If you think about metamorphic rocks, one type of metamorphic process is contact metamorphism. And contact metamorphism recrystallizes the country rock in that metamorphic aureole. Well, in some cases, particularly when that rock is limestone, not only can you produce a marble, but you often have metal-rich solutions coming out and interacting with that marble to create hydrothermal deposits. These are hot water deposits. This is hot water that's being extruded with a lot of silica and things that don't like to merge with other minerals: gold, silver, lead, zinc. Okay. So what we find concentrated in these veins that are the last phase of plutonic activity, intermixed with the metamorphism, are gold deposits and other things as well. And that general ore deposit called a skarn. Okay, and so it's basically a metamorphic aureole that's been enriched in metals. Okay, now that gold, that actually is the mother lode. When you go to a museum and you see these big crystals of gold, they've actually been etched out of quartz veins. And so those big crystals, delicate little finger-like crystals, are from these big quartz veins, many of them from the Sierra Nevadas, which is a batholith, and in particular the quartz veins associated with that magmatic arc back in the Mesozoic. Okay. But it turns out that's not where they were found first. They were found as placer deposits, because as the batholiths were uplifted and eroded, a series of rivers came down towards the Sacramento Valley that carried these heavier gold deposits, and they were deposited in placers. Now, placer is a concentration of heavy or high density minerals by selective deposition. So we'll find them sometimes in the pools of a river or the riffles. Remember, the riffles are those areas that kind of connect the pools. And so gold can be trapped in a variety of places there. And so what did the first prospectors do? They basically concentrated that gold by centrifugal force. They took the sediment from these areas here, and then they concentrated them, and they ended up with a concentrated gold. And so that started the gold rush in California. Now, there's two problems here. The first thing is, once they realized that these gold deposits were in the river deposits, they started using hydraulic hoses to literally wash out huge cliffs of these river deposits. And then they had big flumes and the like. But in the process, they increased the sediment. And remember what we said about increased sedimentation. Quite literally, it started to silt up the harbor in the Sacramento rivers, which also was the capital at the time. And so one of our first legislative responses to increased sedimentation was no hydraulic mining. Okay. But the other thing is, one of the things that you use to help concentrate gold is mercury. And so mercury is an element that is used in this so-called artisanal individual gold mining, that they're basically mining like we did in the 1850s in California. Okay, and the problem with this is that the inorganic mercury is used to recover gold. The problem is that as it rinses out, it becomes a different type of mercury that's altered by biological processes. And so you have contamination from the source downstream. Okay. Actually, contamination both in the soil and in the water that's leaching from that. And so there's a discussion in your book about this. I'll refer you to that discussion, but it illustrates particularly third world problems, or lesser developed countries, now better said, in terms of the techniques that are being used now that have such serious environmental consequences. Mercury actually comes from a variety of places. Tambora, the eruption, we get a big spike there. Look at the gold rush. And this is atmospheric mercury. Literally, so much mercury was being used in that gold mining process that we see a big spike comparable to an eruption. Here's Krakatoa. And then beginning with industrialization, we use mercury a lot, with a little spike with Mount St. Helens. Okay, until recently, take a look what's happened. Okay, we basically have reduced the use of mercury almost to nothing by comparison. Just think of the mercury thermometers that we don't have anymore. Okay, dental instruments, batteries, etc., 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 etc. Although we do have them in some light sources, but because of the serious health consequences of mercury, and the many places, and much of the problem was disposal at the very end, not just mining, but what do you do with that thermometer? What do you do with that CFC light bulb, that mercury filled battery? We've seen the problem, so that we've gone to substitutions. Okay. If you look at the increased use of materials, ores, certainly we are increasing the use of ores, but look at the construction material here. Okay, natural aggregates, which are crushed stone, sand, and alluvium, they're actually the biggest source volumetrically of what we use in terms of minerals, and we use a lot of them. Okay, as far as the stone, it's mainly carbonates. This is the crushed stone. Carbonates, then granite. If you see the term trap rock, think basalt. Okay, so trap rock is basalt. Okay, so we've got a lot of gravel. We've got a lot of crushed rock that we're using. Of course, we're using it for concrete to a large extent. Okay, but one of the other things we're using it is sand for fracking. And so if you look at the amount of sand used for fracking, it's been increasing exponentially. So where does that come from? What is it? What makes a good sand? Well, the thing that makes a good sand is, and actually that makes a good sand it's got to be high silica content. Now, high silica content because it's hard. Okay, it's got to be a homogeneous size and high roundness and sphericity. Because what you want to do, you want to push it into fractures and keep those fractures open. Okay? High crush resistance goes back to why you want high silica content. Low solubility, same thing. Silica is insoluble. Low turbidity, that basically says I don't want a lot of intermixed clay or anything like that. I want it to be well-sorted, well-rounded quartz sand. And I want it to be the density and specific gravity of silicas in case you're using a substitution. So what does that mean? I want a quartzite, or rather quartz arenite, a sandstone or a sand that's 95% or more quartz. And so that's what this is. Now this particular sand is from the St. Peter's sand. It's an Ordovician beach and aeolian sand. Okay? And look at it. It's well-rounded, well-sorted, 100% quartz. Nothing better. Okay? So those areas, those depositional environments are prime mining sources. What you don't want is something like this that's got both quartz and feldspar and rock fragments and matrix. That is a sand that is of no value in terms of fracking. Okay? Now, the other thing is if it's a sandstone, you want it to be highly, easily friable, highly friable, easily disaggregated. You want it to be near surface because you don't want to have, it's just not economic to do underground mining, and you'd like it to be close to where you can ship it to wherever it goes. And it turns out that we have our own sand, the basal Cambrian sand of Central Texas, the hickory sandstone that some of you may have seen on field trips to Central Texas. Now the hickory sandstone is, it's interesting that it's usable. It's sometimes called ground sand because it isn't this pure white sand like St. Peter's. But it has some feldspar, but because of its diagenetic history, that feldspar has been removed. So diagenesis has concentrated the quartz. Okay. The other thing is because it wasn't buried very deep, it's not highly cemented, and so it's more friable. And so the geologic history of that sandstone, in terms of its diagenesis and burial history, and of course its proximity to Texas hydrofracking, has made it a good alternative. And we've got some alternatives. There are synthetic ceramics. There are resin-coated sand. These are basically trying to mimic the quartz sand. They aren't being used a lot now, but they were an alternative to try to meet these criteria when we thought we were running short. Now, what are environmental problems? You don't need to remember this except water, air, and water, and air. Okay, those are the three main ones that, from a scientific point of view, we need to focus on. If you live near there, noise, increased traffic, devaluation of real estate, there are other issues as well. We're not going to deal with that. But what about the water issues? Well, first of all, it's the water used in the mining, and then it's the reuse and treatment of the water, and it's then potential surface groundwater contamination, and therefore requiring water monitoring. Okay. Now, one of the big concerns here is that so much water is consumed by hydraulic fracturing that this becomes a major issue. And so this particular issue is not just the production of the frac sand, but rather the utilization of the frac sand. So these environmental implications overlap with the issues in terms of energy resources. Okay? For air, it turns out that one of the bigger problems is potential dust emission for silicosis. Silica can be a carcinogen, and if you're around a lot of producing this sand or transporting this sand, you've got to be very careful about monitoring and protecting people. The silica dust is a carcinogen, and you need to think about the manufacturing, handling, and use of it. Okay. The other thing is if you use coated propellant, so you use formaldehyde, and that's a potential fire hazard as well as health hazard. The good news is that both silica and these resins are not ecotoxins, and what that means is they're not toxic to the environment, they're just toxic to humans, as if we're not part of the environment, but that's another story. Okay, transportation, it's important, but we're not going to deal with it. Reclamation is an issue, though. We are involved in the reclamation plans, the monitoring, again, things like leaching of the water, reclamation, revegetation of land, etc. Okay, so these are all issues that are directly or indirectly related to the sand as a resource. Another sedimentary process that gives us very economic products that we are self-sufficient in is evaporation and evaporite deposits. I'm not going to get into that right now, but it's not just salt, but it's potassium for fertilizers and gypsum for sheetrock, and it's the alteration that sometimes happens in the anhydrite to give us elemental sulfur, etc. And by the way, that elemental sulfur which occurs at depth, that was the main process by which we put hot water down, dissolve it, bring it up, and reprecipitate it. So when you go to Galveston, you see these great big mounds of sulfur. That's where they came from this fresh process. We're getting increasingly less reliant on that. Now, another process is weathering. Okay, if you remember, I said that aluminum is the dominant, is mainly in feldspars, and in a really hot, humid climate, you can actually dissolve out the silica. Basically what's left is an aluminum oxide. Aluminum oxide is where we get that 35% concentration. And that's basically the weathering product, long-term tropical weathering of feldspars, or better said, igneous rocks that have feldspar in them. So those are our bauxites, and laterites are a similar type of deposit, but we're getting our iron ore, where the iron is being concentrated, and they occur in slightly different portions of the tropics. Okay. We use a lot of material per person, and the thing is, we use it to maintain our standard of living. So, as we've talked about before, what happens when lesser developed countries want to raise their standard of living? Well, they're going to use more of these minerals. Now, the mineral use depends on population, standard of living, and waste. And so the book uses this little thing that the standard of living is proportional to the useful consumption of resources times the useful consumption of energy and ingenuity, technical, political, but inversely proportional to population. Okay? And so if you increase P, you better increase R and E and I more, or you'll never increase your standard of living. And that is, of course, the issue that we're dealing with for the future. Now, we have two responses to this looming problem. It's not just with mineral resources, it's all non-renewable resources. One is that, we'll figure it out. Mineral supplies, mineral supplies are finite. We can't grow more. We can't manufacture more. So we're going to have to figure something out. Or, don't worry about it. We'll never run out because ingenuity, technology will come to our rescue. We will have substitutions. We'll have soft iron versus taconite, or copper wires for communication versus satellites, or fiber optics. That substitutions or alternatives or new sources, we'll always figure it out. Okay. Now, one of the issues that we talked about addressing this problem, though, is the Hubbard curve. The Hubbard curve argues that there is a fixed volume of producible reserves of any non-renewable resource, and that it will eventually peak and decrease. Okay, and that was supported by oil production through about 1997. Now, if you look at that, if you take that volume and you divide it by the rate at which it's being used, to get that volume you have to make an estimate. You can predict the lifespan of that, projected lifetime. And for bauxite, a couple hundred years. We got a lot of it. We don't use it too much. But here, silver, wow, that would be 18 years if we didn't do something. Well, of course, what we do is we recycle. But the point is that if we know what the total volume reserves are, and if we don't change the rate of consumption, which is really production, then we're going to run out. Okay. Well, clearly, we can change all of those. Okay, so let's look how. We'll skip that. We could find more. We could reduce our use. We could replace. We could recycle. We could stockpile. We could do without. Well, let's not do that. Okay, so finding more. Well, certainly by either going to new areas, technology can help. Should we go to the Antarctic? Should we go to Greenland? Should we go to the North Slope of Alaska? These are all things that will help. There's a lead time. You can't just go into a new area and start producing tomorrow. There are typically environmental and economic costs, because usually the stuff that we haven't produced is for a reason. And so just think of oil sands and land disturbed as being a potential issue. We can find more. We can go to Canada and find oil sands, but at what cost? Now, this was the Hubbard curve. Notice it's a little biased because this little hump here is actually finding more. That's Alaska. Okay. Now the argument is, but that's not going to help a whole lot because we're still declining. We just postponed Hubbard's peak a little. That's postponing it. But yeah, maybe we could enhance recovery. That'll help a little. But all we're doing is kind of shaving, or not shaving, but padding the back. Except, let's look at hydraulic fracturing. And there, that technology has literally caused a significant bump. So now we're looking at not this, but this. Having said that, it's still going to bump. It's just we haven't gotten there yet. Okay. If you look at Hubbard's curve, if you consume something rapidly, and let's just say Hubbard's curve in a general sense, what happens if you conserve? Well, what you do, you don't destroy that peak, you just postpone it. But that's good. You postpone the time, and the longer you can postpone that peak, the time to peak, the more time you have to find an alternative. And recycling, well, actually, conceivably, you could recycle 100%. So recycling is at least a possibility. It may cost a lot. It's inconvenient. Some things can't be recycled. Okay. When you look at, though, lead, we're doing pretty good with lead. Not so good with aluminum. Actually, if we were to look at, here's lead. We're up to 60% from about 10% in 1970. Look at aluminum, we're pretty constant. We haven't improved much on aluminum. Okay. So, again, some things we're doing better on, some things we're not. Well, what about a substitute? That might help. And sometimes that works. It turns out there was a crisis in whale oil. The whales were really expensive, and the whales didn't like it. Turns out petroleum was a better source of lighting, or rather fuel. Fossil fuels replaced wood. Fiber optics replaced copper wire. There we have a fair number of significant substitutions. And in fact, the history of energy conservation in the U.S. is one of substitution. We used to burn wood. The Industrial Revolution and internal combustion engines came in. We burned coal with the steam engine. With the steam engine. Then the internal combustion engine came. We started to burn petroleum. We discovered natural gas. We brought in nuclear. We see this continued substitution and a change of mix, so that where we were 100% wood, at one time we were 80% coal. Now we're mainly petroleum and natural gas, and this is going to be the future at some point. Okay. The do without, well, that's risky. But what you can do, you can try to prevent short-term shortages by stockpiling. Okay. And you can also ration. I guess I should have added rationing. But for example, in the 50s, China cut off our tungsten. So we built our own stockpile. We then later sold it off. The oil embargo of 73, 74 led to our stockpiling 93 materials, including oil. Okay. The strategic petroleum reserves, presently we've got about 700 million barrels of oil that are stored there. Okay. North Korea has been exporting 86% of its exports to China, and 88% of North Korea's imports were from China. China threatened to cut off buying coal from North Korea, and they said, that's no problem. We have a lot of graphite and magnesite, and that's important for smartphones, so we're okay. Well, then China said, oh, by the way, we're going to also ban imports of gold and rare earths, as well as export to you jet fuel and other fuels. So you see right now a dynamic going on between North Korea and China. And why is that? Well, we know why it is. We can't escape why it is. It's on the news every night that we're trying to figure out how do you induce North Korea to stop nuclear testing and to give up nuclear weapons. Well, the trick is mineral resources and mineral economics. And the only players right now are China, because they dominate both the import and exports of North Korea. And so we can wish what we want, but the reality is this is mainly presently between China for the reasons that we've talked about. And so this ends our ramble of the implications of mineral resources. It is an interesting game we play, and as environmental scientists, it gives us work to do. So I will post